Okay, Physics 5.1 radiation. I just did this entire lesson, but I accidentally had the mic plugged in the wrong thing. So we're going to start with, we're not going to do this one in the order of the syllabus, we're just going to go to the whole topic since it's so small in logical order. Okay, so we're going to start with atomic structure. So atoms, and hopefully this is more review than teaching, atoms consist of protons, neutrons, and electrons in this little unit that we call an atom, and that unit has two basic components: the electrons that float around the outside of it, and the nucleus, which sits in the middle, that is made out of the protons and the neutrons. A really silly way to think of it, the nucleus is the poop, and the electrons are the flies buzzing around the poop. Okay? So an atom consists of a small nucleus of protons and neutrons surrounded by electrons. You'll find out in a minute why, but an atom always has the same number of protons and electrons. It'll make perfect sense why in a bit. Okay? So the way we write and denote atomic structure and atomic mass. So the atomic number, as we'll call it, is the amount of protons in the middle of that atom or in the nucleus. So for this guy, the atomic number is 3 because he has 3 protons. 1, 2, 3. The mass number is the amount of protons and neutrons. So there's another name, we'll also call it the nucleon number, and that makes sense. If you're Bermudian, you come from Bermuda. So if you're a nucleon number, you come from the nucleus. And the nucleon number is the combination of protons and neutrons added together. So it's everything in the middle. 1, 2, 3, 4, 5, 6, 7. Or you can just add them both together. Okay? So your atomic number or your proton number is just the protons. That's the easy one. The mass number or the nucleon number is everything in the middle. So of course, if you have your nucleon number, you can work out your neutron number by subtracting the protons. Okay, so protons, neutrons, and electrons. You will find your proton in the nucleus. It has a mass of 1, and it's called a relative mass because, of course, these things are very, very, very tiny, so trying to write that in kilograms would be silly. And it has a charge of +1. A neutron is also found in the nucleus. It has a mass of 1, but it has a charge of 0. Neutrons are neutral. And then you have electrons, which float around the outside. It has a mass of, this is a tiny number, we'll just say 0. And its charge is -1. So now that you see the proton and the electrons have opposite charges, it makes sense that this statement is true. An atom will always have the same number of electrons as protons. Atoms have no charge. So if it has 4 pluses, in order for it to be overall no charge, it needs to have 4 minuses. So now nuclear notation, some people say top number and bottom number. Because that can get switched around, we're going to say the larger number and the smaller number. The larger number is everything in the nucleus. So we're looking at this guy, everything in the nucleus. And then the smaller number is just the amount of protons. It can never be the other way around. It just won't make sense. So the larger number is everything in the nucleus, so the protons and neutrons, and the smaller number is just the protons. This could never be the proton number because it's bigger than this number. How can you add numbers to it to make it smaller? Unless you're doing minus numbers, duh. Okay, isotope. Not the hardest concept, but people get it mixed up. Now, an atom has a name based on its proton number. So if it has 6 protons, it is carbon, fact. But the amount of neutrons it has can make it act different. So think of it like your proton number is your last name, and then the neutrons just determine what your first name is. So when hydrogen only has 1 neutron, when hydrogen has no neutrons, it's hydrogen, regular hydrogen. If I start giving it neutrons, which has no charge, so it's not really going to affect it, it just gets fatter. So I make it a little bit fatter. It's still hydrogen, but we call it hydrogen 2 because it's heavier. It's now got a mass of 2. And then we give it another neutron, no charge, but makes it fatter. It has 3, so hydrogen 3. So an isotope is an atom with too many or too few neutrons. Okay? So we'll skip questions. You could just hit pause on the tape. It's 1957. You could just hit pause and try it and check your answer. More questions? Again, hit pause. Alright, so some atoms are what we call radioactive. And what that means, they're giving off radiation. They're decaying. They're giving off energy in some way, shape, or form. So there are 3 types of radiation: alpha, beta, and gamma. Oops, too much. Alright, alpha particles, beta particles, and gamma rays. It is important to remember the difference between particles and rays. Don't get that mixed up. Alright, so alpha, beta, and gamma. Oh, how do you detect radiation? You'll see it on TV. I don't have a slide because I'm prepared for everything. It's called a Geiger counter, and it makes a little clicky noise whenever you are detecting radiation. I'll find it on YouTube once. So now that I think of it, you may not be able to hear it, but let's see what we get. Alright, so there's your Geiger counter. Makes that weird clicky noise. Yeah, so that's...
184,000 times. Well, beta radiation is much stronger. It's not even
Okay, that was fun. So back to the slideshow. So alpha, beta, and that was your radiation detected with the Geiger counter or Geiger molar tube. Feel free to Google that because I don't feel like making a slide. 3 types of radiation. So you have alpha particles, beta particles, and gamma. Now alpha particles are these big, fat, heavy, technically they're the nucleus of a helium atom, and it's just these 2 protons and 2 neutrons stuck together that are moving kind of slow. Alright, they're heavy and they're slow, but they're big, so they still do a bit of damage. In fact, they do a lot of damage. Then you have beta particles. Beta particles are just electrons moving very, 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 very fast. And then you have gamma rays, which is just an electromagnetic wave, that really energetic one on the other side. So penetrating power means how far can these types of radiation get before they collide with too many other atoms and their nucleuses. Nuclei. Okay, so alpha is big, which means when it starts to travel, it bumps into a lot of stuff. It bumps into air molecules, it bumps into dust molecules. It will not get through paper. Beta, a little bit smaller, it will get through paper, but it will not get through a little bit of aluminium. And gamma, there is not even any mass there, it's just energy wave. That'll keep going. Nothing's going to slow that down other than about 3-4 feet of concrete. Okay? So those are basic table, come on now, basic table skills. Draw the table, write it out. A question, you can hit pause if you want to try it. Here comes the answers. Skip this. I should delete that. Now ionization is when an atom loses an electron. In all honesty, it's loses or gains, but let's just say loses. So these electrons are floating around the outside. If I came in like a thief in the night and erase one, good job, buddy. If I came in and just took one of these electrons away, I've just ionized that atom. Now because I have 1, 2, 3 positive charges and 1, 2 negative charges, my atom now has an overall charge of +1. Trying to do this with the mouse is just silly. Alright? So alpha particles, because they're 2 protons and 2 neutrons, they have a charge of +1 already. When they go anywhere near one of these electrons, which are negatively charged, they'll collide with it and steal it. They just like to do that. Beta particles, they'll cause ionization not because they steal an electron, but because they're negatively charged and the electrons are negatively charged. When they get close, they push it away. It's kind of like bumper cars. It bangs into it and knocks it out. And gamma doesn't really do much ionization. It doesn't really care. Okay? Now, magnetic fields. We should start with the other type of field, but let's not. So, gamma has no effect by a magnetic field. It does not care. Alpha and beta are opposite to each other, and they act this way for a reason, mostly because of how beta acts. Now, beta is a stream of electrons. Moving electrons is considered a current. If you have a current cutting through a magnetic field and perpendicularly, of course, it's going to create a movement. That's Fleming's law, I think, or the left-hand rule. So if we have our left-hand rule applied, beta is going to move downwards, and because alpha is opposite to beta, it will move upwards. It's just the way the cookie crumbles. Okay? Please note, alpha moves opposite, but not as much because it's so fat. Now electric fields, very basic, opposites attract. Beta's negative, alpha's positive. They're just going to move, and they'll move based on how much their mass is. Again, questions, go for it. Hit pause, whatever. Moving on. Now we're going to talk about decay. This is where it gets a little bit difficult, so try to pay attention. Or you could just rewind it and watch it again. When you have a gigantic nucleus that is unstable, it tries to become more stable by getting rid of things. Imagine trying to hold too many plates when you walk to the kitchen. The easiest way to get more stable while holding too many plates is just to drop a few. Okay? So alpha radiation is when a big nucleus gives off an alpha particle, which is 2 protons and 2 neutrons. Now, we can write the decay out as like a math equation, but it's almost math backwards. So it gives off 4 particles, right? 2 protons and 2 neutrons. So 238 turns to 234 because it gave off 4. But only 2 of those particles were protons, so that number becomes 90. Another way to look at it is, what can you put there so that something plus this equals that? And it's kind of simple, all right? So alpha can be written as 4-2 and the alpha thing. And you can also write it as helium if you want. Don't know why, because it's a positively charged helium atom, but there you go. Helium molecule, sorry. So there's your question, go for it. Just look at it like backwards math. It's not rocket science yet, or technically it is. Now beta's where it gets a little bit wonky, okay? Beta is caused by someone in the nucleus switching teams. And what happens is a neutron in the nucleus turns into a proton. He switches sides. And in order to become more positive, so the neutron has no charge, it's 0. In order for it to become plus, it has to get rid of its negativity. Think about that in regular terms. In order to become happy, plus, you have to get rid of your sad. Just makes sense. And of course that will work the other way around too. So, this is where it gets a little weird. It suddenly gains a proton. So the original molecule had 6 protons. Now it has 7 because it suddenly gains a proton. You'll notice that my mass number did not change, and that's because this is the sum of P plus N, protons plus neutrons. Technically, even though I lost a neutron and gained a proton, P plus N stays the same because one's P and one's N. It just switched teams. Think of it like a football game. I don't know how many people play football, but let's say there's 6 people on a team. So there's 12 people on the field. If one person switches sides, so let's say it's 6 versus 6, 6 versus 6. If one person switches sides, then there's 7 versus 5. There are still 12 people on the field, but it's 7 and 5. Same thing's happening here. Is it 7 and 5? Yes, I'm feeling a little slow just now. All right, and as a result, we end up with this, which makes perfect sense because the only way for 7 to turn into 6 is to minus 1. Alrighty? Please note, you can also write beta as 0 and minus 1 e because it's just an electron. Now, there's your question. There's your answer. Gamma is just a spoiled brat. Cobalt, very energetic. He's very angry, so he shouts and screams and acts like a big baby. And that meant nothing to anybody. Gamma radiation, 0 and 0. Okay? It's just got less energy now, so it's literally a baby shouting for attention. As per usual, we make things into tables. There's a very quick and simple table. Now, and there's some questions for you. Complete the decay equations. and the answers, of course, you had to hit pause. And again, questions and answers, hit pause. Now, I normally make this into 2, but I feel like I can get through the second part, so let's do, it's either half-life. Let's get through half-life. So the best half-life is the amount of time it takes for the mass of the nucleus, or the count rate from the GM counter. Remember that machine I showed you earlier on YouTube? The amount of time it takes for the mass or the count rate to drop by half due to radioactive decay, not dropping it on the floor. Okay, so the way I explain this is, imagine you had a fridge and your mom went shopping, and every day you eat half of the food in the fridge. So on Monday there are 8 apples. So by Tuesday, well, on Monday you eat 4 of the apples, right? Because every day you eat half. So she went shopping, she had 8, you ate 4. The next day there are 4 apples left, so you eat half, which means you eat 2. The next day there are 2 apples left, so you eat half of what's there again, you eat 1, and of course on this day you eat half, so you eat half. That's what half-life is. And I don't know if there's a formula, I kind of just use common sense, but let's try it with this question. So the half-life of this package of bulk ketchup is 3 days. So every 3 days you eat half of the ketchup. Okay? How long will it take for you to only have 2 ketchups left? So the way we work this out, for every 3 days you go down by half. So 64 to 32, 3 days. 32 to 16, 3 days. 16 to 8, 3 days. 8 to 4, 3. 4 to 2, 3 days. And then you just add them all together. 3, 6, 9, 12, 15. It takes 15 days for your ketchup to go from 64 bottles to 2 bottles. All right? And that can be asked in any way. They can ignore the days and say that it takes 15 days to get from 64 to 2. What's the half-life? You just have to do the same thing. Okay? I wish that was a link, but I'm not smart enough to do it that way. Uses for radiation, that's your assignment. Have fun.